Here is slide number 5 and I am your presenter Asloob Mutassar. What kind of systems are considered in Fourier optics? In Fourier optics we consider isoplanatic systems or the systems under paraxial approximations will be considered. An optical system is very close to aberration or defect-free system when the sizes, I mean that the diameters of the components used are small or small portion of the optic axis is considered, or a small portion of those optical components around the optic axis are considered, satisfying the condition sin of theta is approximately equal to theta, and this theta angle is measured from the object plane to any optical component, okay, or from the image plane to any optical component. So if sin of theta is of the order of theta, then it means that we are working in a region which is called paraxial approximation region, or our system is isoplanatic. Explicit statement is made in the calculation of the field through non-isoplanatic. So when we want to aim over calculation through the non-isoplanatic systems, we shall be talking about, we shall explicitly mention there. Otherwise in Fourier optics we shall assume whether we mention or not that we shall be using isoplanatic systems or the systems under paraxial approximation. The beauty of this system is that we do not incorporate aberrations or defects due to the surface curvatures of the optical components. So small portion or the small diameters of those lenses or the optical components will be used which will satisfy these conditions, that is sin of theta is equal to theta, and you know that we shall be referring such systems as isoplanatic or paraxial, or we shall say that our system is under paraxial approximation. Now you know that once we have studied our systems, we should be able to analyze the quality of the system. The quality of our recorded image or the quality of our optical system will be based on the quality of the recorded image. So if the quality of the recorded image will be compared with the input object. So if they are very close to each other, we shall say that our system, that is designing our system, is very close to perfection. But if there are deviation, then we have to find out some reasons what are the sources of deviations in the optical components. Or the second way that we can analyze our optical system is that by analyzing the imaging system for spatial frequencies allowed by it, and this is referred to as the frequency analysis of an optical imaging system. You know that spatial frequencies means that how many line pairs per millimeter or per centimeter or per inch exist in an object, and our system has passed those spatial frequencies in the object through the optical system undeviated, or are there some deviations? That is, it might be possible if our system is not perfect. It means that the higher order frequencies in the image which corresponds to the edges or the sharpness of some contents in the object will lack, and our system will be compromised in that condition. So the best system is that which allows all the spatial frequencies of the object to pass through the optical system and contribute at the image plane. Now there is another important plane apart from the object plane and the image plane. It is called the Fourier transform plane. It is very important plane, and most of our calculations in the Fourier optics will be based on these Fourier transformation planes, or is called Fourier transform plane. So what is this Fourier transform plane? Let's see where does this exist. If a monochromatic plane wave, now you know that now we are coming back to our monochromatic wave and we are talking about the plane wave. If a monochromatic plane wave is normally incident on an amplitude and phase object, that is our wave incident on object which can change the amplitude of our input wave, or which can change the amplitude of the phase information in that wave which is located, and that object which is we call the amplitude amplitude and phase object is located at the front focal plane of a biconvex lens, then the Fourier spectrum of the object is generated at the back focal plane of the lens, known as the Fourier transform plane or Fourier plane or spatial frequency plane or frequency plane or the spectrum plane. So you know that all these names are equivalent. So we may name them sometimes as a Fourier transform plane, or simply the Fourier plane, or simply the spatial frequency plane, or simply the frequency plane, or sometimes the spectrum plane of the optical system. So you know that here we are talking about the single lens, biconvex lens. So when our system will be complex, we shall be talking about that where our Fourier transform plane exists. But with a single biconvex lens at the front focal plane of which the object exists, and the Fourier transform will exist at the back focal plane of the lens. And remember that this wave, which is we have recorded as the monochromatic plane wave, is a coherent plane wave and is normally incident on the surface. Normally incident mean that the plane of the wave is making an angle 90 degree to the z-axis. So you know that in all our optical systems, we shall draw our optical systems along the z-axis, and the waves will propagate from the left to the right. And we shall be doing our calculations on the Fourier plane or the spectral plane or the frequency plane. Now you see that here we end over slide number 5.